This presentation is on developing a quantitatively accurate reduced-order thermoacoustic model using data assimilation. The work was done by me, Francesco Garita, with a contribution of Hans Yu and under the supervision of Professor Matthew Juniper. It is part of an ITN funded by the European Commission, whose aim is to investigate thermoacoustic instabilities in aircraft engines using machine learning techniques. Thermoacoustic oscillations arise because of the interaction between acoustic waves inside the duct or a combustion chamber and heat release rate fluctuations at the flame. The reason why they are relevant is because the noise and vibrations that appear as a consequence of this interaction can have catastrophic consequences. This has been a relevant problem in the design of jet and rocket engines for a very long time. The fundamental challenge is the very high sensitivity of the growth rate of these oscillations to design parameters, which significantly amplifies small systematic errors present in our models. So we need our models to be as accurate as possible in order to be useful for design. In order to build highly accurate models, we take a qualitative model and use statistical techniques to make it quantitatively accurate using lots of data. We carry out experiments on a simple thermoacoustic system made up of a 1 meter long vertical tube with a diameter of less than 5 centimeters. We then put an electric heater inside it. The heater is made up of 2 ceramic rings wrapped around by many thin filaments and held in place by 2 prongs. This system is known as Ricky tube and is the simplest thermoacoustic system you can imagine. In spite of its simplicity, it contains much of the relevant physics present in a real jet engine. The heat source sets up a natural convection flow through the tube. On top of the main flow, the small acoustic perturbations can propagate. For a tube open at both ends, the first acoustic mode has a pressure node and a velocity antinode at the 2 ends of the tube, and a pressure antinode and a velocity node in the middle. Air flows towards the center of the tube during the compression phase of an acoustic cycle and away from the center during the expansion phase. When the heat source is placed in the bottom half of the tube, it experiences a higher than average velocity during the compression phase, which increases the heat transfer to the flow, and a lower than average velocity during the expansion phase, which decreases the heat transfer to the flow. Typically, there is also a small time delay between the velocity perturbation and the subsequent heat transfer perturbation. The time delay is such that moments of increased heat transfer occur during moments of increased pressure, and moments of decreased heat transfer occur during moments of decreased pressure. In the absence of dissipation, this causes the acoustic energy to grow. The heat source can be either an electric heater or a real flame. Here you can see a premix flame of a few hundred watts made up of ethylene, methane and air. When the flame is put inside an empty tube, it makes quite a loud noise. Let's have a look at it. If you now imagine the same phenomenon on a real rocket engine of a few gigawatts, you can predict what the consequences could be. For our experiments, in addition to the heater, we use 8 thermocouples to measure the centerline temperature and a thermocouple to measure the ambient temperature. Simultaneous measurements are taken every 7 seconds, and by automating the rig, we managed to collect several hundred thousands of data. In our experiment, we changed the heater power in steps of 10 watts, going from 10 watts to 180 watts, and we investigate 4 different heater positions. The first thing we do is model the buoyancy-driven flow. To do so, we use an unsteady conjugate heat transfer model that consists of two partial differential equations, one for the gas and one for the solid, and a momentum integral equation. These three equations are all coupled between each other and depend on three parameters: two Nusselt numbers that characterize the heat transfer from the gas to the wall and from the wall to the surrounding air, and an implicit loss coefficient that quantifies the pressure loss that occurs across the heater. The model assimilates temperature measurements every 7 seconds, and when it does so, state and parameters get updated. We perform data assimilation using the ensemble-Kalman filter, which in the simplest case works in the following way. We start from a prior distribution based on our knowledge, for example a Gaussian distribution, and then we take n samples where n represents our ensemble size. Then each member of the ensemble gets transported to the new state through our model M. Notice that the corresponding new distribution is non-Gaussian if the model is non-linear, like in our case. We then approximate this new distribution with a Gaussian distribution. The estimate of this state, which we call the predicted state, represents the knowledge we have purely based on our model. Next, we build a Gaussian distribution around the temperature measured by the thermocouple based on a standard deviation that comes from experience, for example ±2 Kelvin. Our problem now becomes finding a way to combine these two pieces of information to obtain the best possible estimate of the true state. To do so, we use Bayes' rule. By applying Bayes' rule, we obtain a new estimate of our state that we can use as prior for our next iteration. This procedure can be used to estimate not only the state but also the parameters. So the model simulates the experiment dynamics, and every time experimental observations become available, it updates state and parameters at the same time. The state, in our case, coincides with a long vector of gas and solid temperatures, to which we append the three parameters of our model. As far as the ensemble-Kalman filter is concerned, we find that using an ensemble made up of 30 members is sufficient to obtain accurate results. The ensemble members represent different simulations that run in parallel and interact between each other in the way explained so far. It is worth reminding that the ensemble version of the algorithm is computationally more efficient and easily parallelizable compared to the standard Kalman filter. Here is what the implicit loss coefficient, our first parameter, looks like. Different colors represent simulations at different heater positions. As time progresses, the heater power increases by 10 watts every 70 minutes. After an initial transient, the implicit loss coefficient evolves to a roughly constant value over all the experiments. Notice that for the green and the yellow cases, the thermocouple at the heater location was ignored in the assimilation process because it's affected by radiation, which is not included in our model. That thermocouple represents quite an important piece of information that we miss, as you can see from the deviations of the yellow and the green curves. This is the behavior of our second model parameter, the inner Nusselt number, which quantifies the heat transfer efficiency between the hot gas flow and the inner wall surface. This parameter increases over time, and this is something we expect because when the heater power increases, the heat transfer becomes more efficient. The same considerations hold for our third model parameter, the outer Nusselt number, which quantifies the heat transfer efficiency between the outer wall surface and the surrounding air. From our model, we can infer the inlet flow speed, which increases with the heater power, reaching a plateau at high powers. Notice that the values of this quantity are rather small, around 0.5 meters per second. This means that the Mach number is close to zero, and hence it is reasonable to assume negligible mean flow speed when developing the acoustic model. Here is instead a single-time snapshot of the gas temperature profile for the 4 heater positions investigated in the study. You can see that the ensemble Kalman filter updated state and the experiments match quite well. The gas temperature at each time step and at each axial location is what we are ultimately interested in, because it's needed to compute the sound speed inside the tube, which, together with the inlet flow speed, represents our input to the acoustic model. The experiments described so far do not include only thermocouples and electric heater. In fact, the full experiment is much more involved because it includes also a loudspeaker placed at the bottom of the tube, which provides an acoustic ping every 7 seconds. In addition to the loudspeaker, a set of 6 probe microphones is installed on the rig, by means of which we measure the pressure inside the tube continuously at a frequency of 10,000 Hz. This picture shows one of the acoustic pings we provide through the loudspeaker and the following decay as seen by the 6 microphones. We use the microphones to measure decay rate and frequency of the oscillations in the decaying part of the signals. In the top right corner, you can also see the magnitude of the normalized 6 complex pressures and the corresponding pressure eigenmode, which, for a tube open at both ends, has a pressure antinode in the middle of the tube, as shown before. The way in which we compute the decay rate and the frequency of oscillation is the following. First, we filter the signal. Then, we apply the Hilbert transform. This gives us the frequency of oscillation. If we then take the logarithm of the resulting signal and we fit a straight line in the decaying region, delimited by the 2 vertical dashed lines, we obtain also the decay rate, corresponding to the slope of the best fit line. This procedure is applied to each microphone, and the 6 values are then averaged to obtain a more robust estimate, although no significant scatter exists between the 6 measurements. The average decay rate and frequency represent the real and imaginary parts of the complex frequency S, respectively. The second step for us is the modeling of the fast timescale, the acoustic timescale. For this, we use a network model made up of 50 acoustic elements. In each of these elements, we solve the Euler equations in the assumption of no mean flow because, as we saw before, the Mach number is close to zero. The solution of these equations in each element is obtained by performing a Riemann decomposition, which results in an F wave traveling downstream and a G wave traveling upstream. Different elements correspond to different waves. We then connect adjacent elements by specifying the jam conditions at the interface between 2 elements. For an empty tube, the jam conditions represent the viscous and thermal acoustic losses in the boundary layer, which are obviously distributed losses, but which we model as concentrated losses. Notice that the 2 coefficients highlighted in red are fully known because they are only a function of geometry, fluid properties, and oscillation frequency, which we know. So the question is, since we know the model parameters for the empty tube case, how do we use this model? Well, we first perform some experiments in the empty tube case, and then we use these experiments to infer the boundary conditions, the only unknown of our problem. This translates to inferring the reflection coefficients at the 2 ends. Throughout all this study, we assume the 2 ends to be identical and therefore characterized by the same reflection coefficients. The reflection coefficients can also be computed from experiments using the multi-microphone method, but this is something we do not do in this study. Instead, we assume constant reflection coefficients. Now we know everything about our empty tube. What do we do next? The next step is to introduce the electric heater in our acoustic model. This translates to adding an additional acoustic element at the heater position with the corresponding jump conditions. The way in which the viscous and thermal acoustic losses across the heater are modeled is by using a model made up of 4 parameters highlighted in red. Unlike before, these 4 parameters are unknown to us, so we need to infer them from experiments. Likewise, we model the 8 thermocouples inside the tube by adding 8 additional acoustic elements. We assume the thermocouples to be identical. The model for the thermocouples is simpler compared to that for the heater because it does not involve time delays. So now we have a full acoustic model that relies on 6 parameters in total, which we need to infer. In fact, the independent parameters are only 5 because the viscous to thermal loss ratio for the thermocouples is assumed to be the same as the viscous to thermal loss ratio for the heater, for simplicity. To infer these 5 independent parameters, we perform lots of new experiments with the heater inside the tube switched off, placed at different locations with and without thermocouples. For each experiment, we measure temperatures, decay rates, and frequencies. The result of this process is shown in these figures, where you can see a comparison between experiments and modeled predictions of the decay rates in the top figures and of the frequencies in the bottom figures, and this for different heater positions. The left figures represent the case of no thermocouples, whereas in the right figures the thermocouples are present. You can see the additional drag due to the thermocouples in the top right figure, where the curve is shifted downwards compared to the top left figure. The model parameters are inferred by simple regression and are reported in the figure captions. As you can see, the agreement between experiments and the physics-based model predictions is very good. The last step for us consists of modeling the thermoacoustic effect that occurs when we switch on the heater. For this, we need to know the speed of sound in each acoustic element as well as the inlet flow speed, computed in the first part of this work using the ensemble Kalman filter. We test 2 similar thermoacoustic models where the normalized heat release rate fluctuations are assumed to be proportional through a coefficient n to the normalized acoustic velocity fluctuations and time delayed with respect to them by a quantity tau. The first model we test assumes that these 2 parameters are constant, whereas the second one assumes that tau is inversely proportional to the inlet flow speed. When we switch on the heater, we perform experiments at 4 different heater positions and investigate heater powers up to 180 watts in the way described earlier. With these experiments, we train our 2 thermoacoustic models and infer their parameters. Here you can see the comparison of experiments and model predictions of decay rates and frequencies for the 2 thermoacoustic models, one on the left and one on the right. Both models actually give satisfactory results, although the first one seems to perform slightly better. Notice that we found a value of k tau for the second model of about 2, which is very close to 1, the theoretical value. This brings me to the conclusions of this work. So what did we do? We built a reduced order thermoacoustic model in a step-by-step fashion, using physical principles and training it using more than 100,000 experiments. We saw that by automating a laboratory rig, you can perform thousands of different experiments which can be used in conjunction with data simulation tools in order to build faithful models. In the future, we plan to replace the regression part with more advanced statistical learning techniques, such as the Markov chain Monte Carlo method, and we are already working in this direction. Furthermore, we plan to couple this work with a joint methods so that Once we have a faithful model of the system, we can work out the best way to design out thermoacoustic instabilities using adjoint-based sensitivities.